Hello, welcome to Physics 220, Classical Physics 2 at Iowa Western Community College. This is going to be an online course, and we start this course with Chapter 17, Temperature, Thermal Expansion, and the Ideal Gas Law. In this chapter, we cover atomic theory of matter, temperature and thermometers, thermal equilibrium and the zeroth law of thermodynamics, thermal expansion, thermal stress, the gas laws and absolute temperature, and the ideal gas law. Section 1, Atomic Theory of Matter. Atomic and molecular masses are measured in unified atomic mass unit U. This unit is defined so that the carbon-12 atom has a mass of exactly 12.0000 U. If we want to express a U in kilograms, 1 U is equal to 1.6605 times 10 to the power minus 27 kilogram. And for reference, atomic mass of natural hydrogen is 1.0079 U. On a microscopic scale, the arrangements of molecules in solids, liquids, and gases are quite different. For example, on the right here, we are demonstrating these different phases of matter. As we can see on the top, we see the spheres are representation of atoms, and the lines are the connection between the atoms, and this is like the atomic bonds holding these spheres of atoms together. For a solid case, we have a well-positioned structure of atoms, which defines the crystalline, molecular, or atomic structure. For the liquid case, in the middle one, we will have less distance between the atoms or molecules, but in a more packed structure. And also the arrow demonstrates the direction of their movement. So it shows each molecule is freely moving in different direction in 3 axes of movements. In the third one, we will see more distances between atoms or molecules here, and they're more free to roam around and move and collide together. And this is a representation of a gas. So the top one is the solids, the middle one is a liquid, is a representation of a liquid, and the last one is a representation of gas. All right, as an example, let's take a look at problem number 2 from the book. It asks, how does the number of atoms in a 31.5 gram of gold ring compare to the number in a silver ring of the same mass? So basically here is asking about the ratio between the number of atoms in 2 different objects of 2 different materials, but the same mass, 31.5 grams. And we know that the number of atoms in a pure substance can be found by dividing the mass of the substance by the mass of a single atom. And the mass of a single atom, or atomic mass, of gold and silver can be found from periodic table. So we will write a number of U atoms, which is gold, divided by number of Ag atom, which is silver. And we should take a ratio of, as I said, the mass of the substance, which is 31.5, and we should convert it to kilogram, which is times 10 to the minus 3 kilogram, divided by the mass of atomic mass of U, or gold, which is from the lookup table 196.966570 U divided by atom, and we can convert atomic unit U to kilogram, as I said from the first slide, 1.66 times 10 to the minus 27. This is kilogram per U. Okay. From Ag, or silver, we have the same as 31.5 gram times 10 to the minus 3, convert gram into kilogram, divided by the atomic mass of silver, which is 107.86 0.82 U divided by atom multiplied by conversion of U to kilogram, which is 1.66 times 10 to the minus 27 kilogram per U. As we can see, most of these parts will be canceled out, but what we will have at the end is simplifying of the numerator as 107.8682 divided by 196.96670, and the ratio, if we take it, gives us 0.5476. So we can write it down as number of atom in gold is equal to almost half of the number of atom in silver. Oops, Ag, sorry. So this is the answer. And that makes sense because the gold atoms are heavier, therefore we need a less number of silver atoms to gain the same mass. Section 2. Temperature and thermometers. Temperature is a measure of how hot or cold something is. Most materials expand when heated or contract when getting cold. Thermometers are instruments designed to measure temperature. In order to do this, they take advantage of some property of matter that changes with temperature. Common thermometers used today include liquid in glass type, as we can see on the left, and the bimetallic strip, which you can see on the right. And they both work based on the expansion and contraction of material as they get colder or hotter. Temperature is generally measured using either Fahrenheit or the Celsius scale. The freezing point of water, as most of you must be aware of, is 0 degrees Celsius or 32 degrees Fahrenheit, and the boiling point of water is 100 degrees C or Celsius or centigrade or 212 degrees Fahrenheit. As a simple example, I look at problem number 4 from the book. It says among the highest and the lowest natural air temperatures ever recorded are 136 degrees Fahrenheit in a desert and minus 129 degrees Fahrenheit in Antarctica. What are these temperatures on the Celsius scale? So basically, it's asking you to convert these temperatures from Fahrenheit into degrees in Celsius. And we know from the book that equation for the temperature, degrees C, is 5/9 multiplied by the degree in degrees Fahrenheit minus 32. So we plug in these numbers for the high temperature. So for the high temperature of 136 degrees Fahrenheit, we say the temperature in degrees Celsius is equal to 5/9 136 minus 32, and these are in Kelvin, and they are converted into degrees Celsius, and it gives us 57.8 degrees Celsius. And for the low temperature, which was minus 129 degrees Fahrenheit, we converted to degrees Celsius as 5/9 minus 129 minus 32, and that gives us minus 89.4 degrees Celsius. Section 3. Thermal equilibrium and the zeroth law of thermodynamics. When two objects are placed in thermal contact, they will eventually come to the same temperature. When they do get to the same temperature, we say that they are in thermal equilibrium. The zeroth law of thermodynamics therefore says that if two objects are each in equilibrium with a third one, they are both also in thermal equilibrium with each other. Section 4. Thermal expansion. As we said before, typically material expand as they get heated. For example, here we have a cylinder with an initial length of L naught at the initial temperature T naught. When the temperature increases to the new temperature T, the length will be increased by the amount of delta L, which is the change in the length, and the new length will be called L. So L is equal to the initial length L naught times 1 plus alpha delta T, and alpha is the coefficient of linear expansion, and the unit would be 1 over degrees Celsius. Similarly, we can have volume expansion, except that it is relevant for liquids, gases, and solids. Delta V here, as the change in the volume, is equal to beta V naught, which is the initial volume, times delta T, the changes in the temperature. And beta is the coefficient of volume expansion, and the unit is the same as linear expansion. But we can say beta for solid is equal to 3 alpha. Water behaves differently for most other solids in terms of thermal expansion. Its volume becomes minimum when the temperature is around 4 degrees Celsius. And as we make it cooler, and as the water cools down further, it starts expanding. As anyone who leaves the butter in the freezer, you must have noticed that it starts to deform the bottle and expand from 4 degrees to the temperature of freezing water at 0 degrees Celsius. This behavior can be seen here, that as the volume is decreasing until 4 degrees Celsius, and as the temperature is going from 4 degrees to 0 degrees, the volume starts to increase. On the other hand, we can look at the density, which is the amount of mass per volume. And we can see the mass is the same, but the volume is increasing, therefore the density is decreasing. That's why the ice is floating on water. Okay, let's look at problem number 20 in the book. A brass plug is to be placed in a ring made of iron. At 15 degrees Celsius, the diameter of the plug is 8.756 centimeter, and that of the inside of the ring is 8.742 centimeter. They must both be brought to what common temperature in order to fit? So in order to solve this problem, we should extract the coefficient of thermal expansion for brass and iron. We know it from the textbooks and from the literatures that we can say, let's put it here, sorry, alpha for brass is equal to 19 times 10 to the minus 6 per degree Celsius. We write it like this. And the coefficient of expansion for iron is 12 times 10 to the minus 6 per Celsius. Write it like this. So the new lengths, or the new size of iron, which we call it the initial length of iron plus delta L, should be equal to the initial length of brass, or the size of the diameter, plus delta L for brass, right? And if you plug in the values for delta L, that delta L is equal to alpha L naught delta T. Remember that we had L equals to L naught times plus alpha delta T. So we call it L naught plus alpha L naught delta T. And we call this guy here as delta L. That's how I written down this equation to delta alpha is equal to alpha L naught delta T. Okay, let's say we erase this stuff from here. We know it from before. And now let's continue from this problem. So we can solve it for the lengths of iron plus alpha of iron, L naught of iron, delta T is equal to L naught of brass plus alpha of brass times L naught of brass times delta T. So we can solve this for the common change in temperature, because this is the common temperature and both of them at 15 degrees Celsius. So we want to get to a new temperature. So what we should see, what is delta T? So this is, we're going to solve it for delta T. So we call it delta T equals to L naught of brass minus L naught of iron divided by alpha of iron times L naught of iron minus alpha of brass times L naught of brass. And if we plug in the numbers, let's see what we get. So let's put here 8.756 for brass minus 8.742. These are in centimeter for iron, divided by, plug in the numbers here, 12 times 10 to the minus 6 per Celsius for iron times 8.742 centimeter minus 19 times 10 to the minus 6 per Celsius multiplied by 8.756 centimeter, right? And if we simplify everything here, so delta T, which is equal to final temperature minus initial temperature, is equal to minus 222, and the unit is degrees Celsius. We know the initial temperature was 15 degrees Celsius, so we can solve this guy for the final temperature of minus 210 degrees Celsius. So both of them should be lowered to the new temperature of minus 210 degrees Celsius in order to fit. Section 5. Thermal stresses. A material may be fixed at its end and therefore be unable to expand when the temperature changes. It will then experience a large compressive or tensile stress, sometimes referred to as thermal stress, when its temperature changes. The force required to keep the material from expanding is formulated as delta L equals to 1 over E times F over A times L naught. L naught is the initial length, F is the force divided by A is the area, and E is the Young's modulus of the material. And from the previous section, 17.4, we know that delta L is equal to alpha L naught delta T. So if you plug in these numbers, F over A, which is the stress, is defined, or we can written as alpha times E, Young's modulus, times delta T, changes in temperature. Section 6, the gas laws and absolute temperature. The relationship between the volume, pressure, temperature, and mass of a gas is called an equation of state. We will deal here with gases that are not too dense, and we call them ideal gases. Boyle's laws state that the volume of a given amount of a gas is inversely proportional to the pressure as long as the temperature is constant. Or mathematically, we can write it down as V is proportional to 1 over P, pressure. Volume is inversely proportional to pressure. And here is the PV diagram, or pressure versus volume, and the relation, as you can see, is reciprocal. We can also see that the volume is linearly proportional to the temperature, as long as the temperature is somewhat above the condensation point and the pressure is constant. Extrapolating the volume, we will see that the volume becomes zero at the temperature of minus 273.15 degrees Celsius, and this temperature is called absolute zero. The concept of absolute zero allows us to define a third temperature scale, the absolute or Kelvin scale. This scale starts with 0 Kelvin at absolute zero, but otherwise is the same as the Celsius scale. Therefore, the freezing point of water is 273.15 Kelvin, and the boiling point is 373.15 Kelvin. Finally, when the volume is constant, the pressure is directly proportional to the temperature. Let's take a look at problem number 30 in the book. It's a simple conversion problem. What are the following temperatures on the Kelvin scale? 58 degrees Celsius, 85 degrees Celsius, Fahrenheit, minus 55 degrees Celsius, and 5100 degrees Celsius. Let's start with the equation for part A. A degree in Kelvin is equal to degree in Celsius plus 273.15. So 58 degrees Celsius plus 273.15 gives us 331 Kelvin. Part B, 86 degrees Fahrenheit. Temperature in Kelvin is equal to 5/9 times temperature in Fahrenheit minus 32, and this part converts it into Celsius. We should add it the 273.15, and if we simplify it, it gives us 303 Kelvin. Okay. For C, let's talk about minus 55 degrees Celsius. Temperature in Kelvin equals to temperature in Celsius again plus 273.15, and this gives us 218 Kelvin. Okay. D, 5100 degrees Celsius, and the same is 30. 5100 degrees Celsius plus 273.15, and this gives us 537.15. 373.15. It's almost 5400 degrees Kelvin. Section 7, the ideal gas law. We can now combine the three relations just derived into a single relation. So we said pressure is proportional to temperature, volume is proportional to the temperature, and pressure and volume are inversely proportional. So we can put them together and say the multiplication of pressure and volume is proportional to temperature linearly. What about the amount of gas preserved? So if the temperature and pressure are constant, the volume is proportional to the amount of gas. With this argument, we can say P times V, or pressure times volume, is proportional to the mass, or the amount of the gas involved into the system multiplied by the temperature. Now, in order to define a unit or a measure of the amount of gas in our system, we define mole. A mole, simply written as MOL, as mole, is defined as the number of grams of a substance that is numerically equal to the molecular mass of the substance. For example, 1 mole of hydrogen molecule has a mass of 2 grams, or 1 mole of neon has a mass of 20 grams. And 1 mole of CO2 molecule has a mass of 44 grams. The number of moles in a certain mass of material is written as N as the number of mole is equal to the ratio of mass in grams divided by molecular mass in gram per mole. That gives us the number of moles. We can now write the ideal gas law. Pressure times volume equals to number of moles times R times T. And here R is universal gas constant, which converts the proportionality equation into an equality. And N is the number of moles. So PV equals nRT is the ideal gas law equation. And R, the universal gas constant, is equal to 8.314 joules per mole times Kelvin, or 0.0821 liter times atmosphere divided by mole per Kelvin, or equal to 1.99 calories per mole times Kelvin. Section 8. Problem solving with the ideal gas law. Standard temperature and pressure STP is defined as temperature at 273 Kelvin or 0 degrees Celsius, the pressure at 1 atmosphere or 1.00 atm, which is equal to 1.013 Newton per meter cube, or equals to 101.3 kilopascal. Volume of 1 mole of an ideal gas is 22.4 liters. If the amount of gas does not change, we can write down the equation of ideal gas in the initial condition of the ideal gas should be equal to the final condition, or P sub 1, the first pressure, times the V sub 1, the first volume, times T sub divided by T sub 1, which is defining the initial condition, is equal to P sub 2 V sub 2 divided by T sub 2, which is the final condition. Always measure T in Kelvin, and P must be the absolute pressure. Let's take a look at an example, problem number 40 in the book. A scuba tank is filled with air to a gauge pressure of 202 atm when the air temperature is 29 degrees Celsius. A diver then jumps into the ocean and after a short time on the ocean surface checks the tank's pressure and finds that it is only 191 atm. Assuming the diver has inhaled a negligible amount of air from the tank, what is the temperature of the ocean water? Alright, to solve this problem, we should do a couple of assumptions. We know that the mass of air is not going to change from point to point from different locations at different temperatures. Also, the volume of air is going to be unchanged since the tank is a rigid box or container. Using the ideal gas law, we can solve this problem, but consider that the gauge pressure is given, but we should convert it into absolute pressure to be plugged into the gas law equation. So we say P1 V1 divided by T1 is equal to P2 V2 divided by T2. As we said, the volume is going to be constant, so cancels out, and we can write down this or solve this one for T2 because we want to see what's the second or the temperature of the ocean water, and it's equal to T1 times P2 divided by P1. Now let's plug in the numbers. For T1 we say, let's write it down here, T2 equals to, for T1 we say 200, let's convert it to Kelvin. 273 plus 29 degrees. And this is in Kelvin. This is in Kelvin. Multiplied by 192 atm divided by 202 atm. Okay, and considering this ratio, it simplifies to 286 Kelvin, and if you convert it back from Kelvin to degrees Celsius, we're subtracting 273 degrees, it gives us the 13 degrees Celsius. So the temperature of the ocean water is 13 degrees Celsius. That's why the pressure of the container or the gas tank has been dropped, because the temperature is reduced. Section 9. Ideal gas law in terms of molecules. Avogadro's number. Since the gas constant is universal, the number of molecules in 1 mole is the same for all gases. That number is called Avogadro's number, and it's written as N sub A, or Avogadro's number, is equal to 6.02 times 10 to the power 23. With that definition of Avogadro number, we can rewrite the ideal gas in terms of the number of molecules. So we can write down PV equals nRT in terms of the number of molecules, and write down instead of little n, write down capital N divided by the Avogadro number multiplied by RT. And if we rewrite this equation and do some redefinition, we can say PV is equal to capital N, number of atoms or molecules, times little k times capital T, temperature. And little k is called Boltzmann number or Boltzmann constant, and it's defined as the constant of gases divided by Avogadro number, or R divided by capital N sub A. And if we plug in the values for constant of gases, R, and N sub A, we will have little k, or Boltzmann constant, as 1.38 times 10 to the power minus 23 joule per Kelvin, and this is this I unit. Okay, now let's take a look at problem number 58 from the book. Estimate the number of A, moles, and B, molecules of water in all the Earth oceans. Assume water covers 75% of the Earth to an average depth of 3 kilometers. So to solve this problem, we imagine that the thickness or the depth of the water on the surface is negligible, or is very small compared to the radius of Earth. And this is, suppose that this is the depths of the ocean, the average depths of the ocean, and this is the radius of Earth. So what we can say, the volume of this area here, which is, we're going to consider the volume of water around the Earth, or the oceans, basically the water in the oceans. We can say the volume is basically the surface of the sphere of the Earth multiplied by the average depth, that we call it the H here, the average depth of this ocean. So we call this volume as pi r squared multiplied by H. This is the estimation we can say, because this is going to be the surface of water on Earth, which is the surface of a sphere, multiplied by the height or the depths of this ocean, or the average depths of this ocean or water around the Earth, and that is giving us the volume. But also we say we are not covering all the surface of air, but only 75%. That's why we have to multiply everything by 0.75 to give us the volume of water around the Earth. So let's plug in the numbers. Let's put 0.75, which is here, multiplied by pi r, and r is 6.38 times 10 to the 6 meter. Let's cube it, and multiplied by the average depths of water, which is 3 kilometers. 3 times 10 to the power 3 meter, and this gives us 1.15 times 10 to the power 18 meter cube. Okay, so this is the volume. Now we have to convert this volume into either moles, or the number of moles, or number of molecules. So from the equation we know we have to convert the volume and say how many kilograms of water we have, and then convert from kilogram into moles. So let's do that. So for part A, let's say 1.15 times 10 to the power 18 meter cube. Let's convert volume to mass, or kilogram of water, which is 1025 kilograms per meter cube, multiplied by 1 mole divided by 18 times 10 to the power minus 3 kilogram, to convert from kilogram into mole. And that simplifies to a number of, let's erase this, number of 6.55 times 10 to the power 22 moles, or roughly 7 times 10 to the power 22 mole. Okay, for part B, the number of molecules, we should use the equation for Avogadro's number, and we say because we know the number of moles, and let's put the exact value, 6.55 times 10 to the 22 mole, and let's do the Avogadro's number, 6.02 multiplied by 10 to the power 23 molecules per 1 mole, and that gives us roughly 4 times 10 to the power 46 molecules. That's a crazy large number, unimaginable. Summary of Chapter 17. All matter is made of atoms. Atomic and molecular masses are measured in atomic mass units, U. Temperature is a measure of how hot or cold something is, and is measured by thermometers. There are 3 temperature scales in use: Celsius or centigrade, Fahrenheit, and Kelvin. When heated, a solid will get longer by a fraction given by the coefficient of linear expansion. The fractional change in volume of gases, liquids, and solids is given by the coefficient of volume expansion. The ideal gas law is given by pressure times volume, or P times V, equals to nRT, or the number of moles, times gas constant times temperature. 1 mole of a substance is the number of grams equal to the atomic or molecular mass. Each mole contains Avogadro's number of atoms or molecules.